All right, now we're on part C, and I need to go find the answers. Here you go. So Blake is sending a wave, pulls toward the wall, and you can see it's going towards the wall, and then when it comes back, it bounces back inverted. And now he sends the wall toward the end of the spring. The other end is attached loosely on a pole, and when you can see the wave is coming back the same orientation, actually even a little bit bigger. It's got bigger amplitude. And then in part C, Blake and Carlos are going to send waves to each other, and it looks like they pass through each other and constructively interfere, make one big wave, and then they pass through each other. And so when we're at the fixed end of a wall, the wave pulses are inverted. When we're at an open or free boundary, wave pulses are not inverted or are upright. And when the pulses overlap, they add together. The principle is superposition, another vocabulary word, and then they pass through each other. All right, Dominique watches what is happening as the two moves. States that the two wave pulses traveling opposite directions, they reflect off each other and go back the way they came. What is wrong with this statement? So they don't reflect off each other and go back the way they came. They pass through each other and they add together. And so one way that you could prove that, this may be coming up later, I don't know, I haven't actually looked at this stuff ahead of time. What if Blake had sent an upright wave to Carlos, but Carlos sent an upside down wave in that string to Blake? Then if they bounced off each other, they would get their own wave back, right? That's what Dominique is saying. But if they passed through each other, each would get the other one's wave. And you could see that. You could see that Blake was not getting an upside down, or Carlos was not getting an upside down wave. He was getting a right side up wave, and vice versa. Now we're in part D, but it's only been 2 minutes. The pair of pulses travel toward each other at equal speeds. The composite wave forms as they pass through each other and interfere at 1 second intervals. And so sketch a construction for the two wave pulses in each column. So this is a very common problem in AP exams. What does it look like when they build together? And so here you can see the answer is that you have, if in the first column, if one is meeting a +1 is meeting a +1, when they meet together, they'll make a +2, and then they'll pass through each other. When a +1 meets a -1, they will cancel each other out right here, right? As they come together, they start canceling each other out, and then they pass through each other. And then if you have this weird looking stair graph meeting this upside down graph, then when they meet together, you will get some very odd sort of interference when they come together. And so that's your bonus extra super hard one. And rectangular transverse waves are traveling toward each other. So you can actually make waves like this on oscilloscopes, in case you're wondering where they got these funky waves. The grids shown in the background are identical and then very highly. So rank the maximum amplitude of the string at the instant of when they overlap. So let's see. We've got 2 + 4 is going to be 6. That's A. Then we have 2 + 2 in B. That's going to be 4. Then we have 2 - 2 in C. That's going to be 0. Then we have 2 - 2. That's going to be 0. So A is greater than B because 6 is greater than 4. 4 is greater than C is greater than D. D is going to be absolutely flat and 0. C is, so when at the centers of the two pulses overlap. So when the center of the top one on C is over the center of, there will actually be a little bit sticking out of each side of it, which is -2. So I guess that's why it's bigger. A is the greatest. B, C and D destructively, there's total destructive interference, and there's still amplitude of magnitude 2. So even though it's upside down, they still say the magnitude is 2. All right, we're in part E. A long elastic cord carrying a traveling wave. It's fixed at position x = 0. And depicts a wave in the beat at time t = 0. And so there it is. And there's your explanation. What the period is At t equals 1 second, the bead is at the bottom of the oscillation, and then it's at the bottom again at t equals 5 seconds. Oh, I see. You can see that right here. At 1 and 5, it's at the same place, so the period is 4 seconds, so the frequency is 0.25 hertz, 1 over 4. The distance from one peak to another is 20 meters, so we can get that off of the top graph. The distance between that peak and that peak from -5 to 15 is 20. So the wavelength is 20, the frequency is 0.25, the speed is 5. And we're still on part E. So what will happen is the bead will bob up and down. The wave will go back and forth because that's what a transverse wave does, but the bead will actually just bob up and down more like this. And here's what's happening. If the amplitude is 0.4 meters, then the bead is going up 0.4, then down 0.4, then up 0.4, then down 0.4. Waves occur because one end of the elastic cord is connected to a mass much heavier than the cord, and so it's an oscillator, and it goes boing, 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 boing. She wants to change waves at the peaks in the graph above are closer together, but the graph above left is unchanged. The peaks on the right are closer together, but the left is unchanged. Tension and the amount of mass must be changed. State how the tension and mass must be changed. To make the bottom graph, to make the peaks closer together, the period needs to be shorter, which is same as saying the frequency should be larger. You can change the period of a spring by changing the mass to be less. So put less mass on the spring, and that will make the period decrease. That will give you a higher frequency. It will also change the graph on the top because it tells us about the wavelength. To keep the wavelength the same while increasing the frequency, the speed must also increase. It's related to the tension. So therefore, we need the speed to be larger. The tension must also need to increase. So increase the tension and decrease the mass. All right, now we're in part F, and we're at 7 minutes, so let's stop.